So in the last video, or the last few videos, we looked at how to calculate molar solubilities in solubilities. And we were always working with water where we didn't have any ions in common with what we're trying to dissolve. In fact, I use the word common specifically there because sometimes we will dissolve an ionic compound in a solution that already has an ion in common. So it already contains one of the ions. And we're going to find that the solubility is greatly reduced. So, for example, if we want to know the molar solubility of calcium fluoride, which we've already done, but not in water, but instead in 0.1 molar sodium fluoride, then we're going to find that the solubility is going to be incredibly low compared to when we just dissolved it in pure water. And why is that? Well, if we start by looking at the solution we're dissolving it in, so the sodium fluoride, we know that sodium fluoride is incredibly soluble, and the sodium fluoride is essentially 100% breaking down and forming sodium ions and fluoride ions. You might say, well, how do we know that? Well, the solubility rules we learnt in the first semester said that all sodium salts are incredibly soluble. In fact, you can pretty much always assume that if you've got any sodium salt, it's going to completely break down. In fact, let's pull up that solubility table just to take a quick peek again. Okay, so here's the top half of it. So notice lithium, sodium, potassium, ammonium, all these compounds are soluble with absolutely no exceptions. The same with nitrate and acetate, no exceptions at all. So these 6 ions will always dissolve unless you're in incredibly high concentrations. You can always assume these things will completely break apart. There's no equilibrium needed. These are kind of like our strong acids we saw in the last chapter. They break down. We don't really write an equilibrium constant for it. If there is one, it's so large we can basically just assume it's infinitely large. A 0.1 molar solution of all of these are all going to be completely broken down. So in terms of concentrations, if it completely breaks apart, we know that every sodium fluoride is going to make an equal number of sodium and an equal number of fluoride because it's 1 to 1 to 1 stoichiometry. If it isn't that, we'll have to remember to double or triple it. We're going to have already fluoride in 0.1 molar concentration. Alrighty, so what is the common ion going on here? Well, calcium fluoride, remember the KSP reaction is when we take the solid and we break it down into ions that can dissolve. So you have to remember your ions and your polyatomic ions and your charges. And here's my ice chart. We're going to calculate a solubility. So we're going to break down S moles per liter here in a later stage. All right, so initially when we're dissolving it in pure water, we said there's no calcium and there's no fluoride. But if we're dissolving it in a solution that already contains fluoride, right, I got to erase that and I've got to rewrite its concentration, so 0.1 moles per liter. All right, now I'm going to let it dissolve, and I'm going to let it dissolve, and of course, if this goes down, this will go up by the same amount here, and it'll go up by double the amount on the other side, so plus S plus 2S. Okay, at equilibrium, I sum together the initial and the change, and here's the first case where the initial is not 0, so I have to go ahead and take my initial 0.1 and add to it 2S. All right, this is going to greatly change the solubility. In fact, before we do a calculation, we can think about it from a Chatelier point of view. So if we disturb this equilibrium by increasing this concentration of fluoride by using a common ion, this increased concentration is going to want to push the equilibrium back in the opposite direction. So it's going to want to dissolve even less than before. So we should expect to see solubilities that are much smaller than we saw in the last segment. Okay, so just push it up a little bit. All right, so we're ready for the calculation. So we're going to say our equilibrium constant, KSP, which we saw in the last section, right, was 1.46 times 10 to the minus 10. It's not very soluble at all. And that's equal to the concentration of calcium at equilibrium, right? That's the saturated concentration, times the concentration of fluoride at equilibrium, 0.1 plus 2x. And because we've got 2 fluorides in the equation here, we're going to be squaring that concentration. And that is yucky, right? So that's the technical term because we're going to have s squared and s's. We're going to have s cubed. We're going to have a cubic equation here. So cubic equations are tough to solve. So what we're going to go ahead and do is we're going to make an assumption that 2s is going to be much smaller than 0.1 so that when we add a very small number to a very big number, we can basically just ignore the small thing and stick with the big thing. All right, so what does that get us? So now we're going to say that's approximately equal to s times by 0.1 squared. So if we wanted to calculate S, then it is KSP, 1.46 times 10 to the minus 10 over 0.1 squared. So 0.1 squared is 0.01. That's like dividing by 0.01 is like multiplying by 100. So that's 1.46 times 10 to the minus 8. That's a molar solubility, so I should put moles per liter. Is our assumption valid? Is 2s much smaller than 0.1? Well, even if we double that number, right, it's barely going to be like 10 to the minus 8 still, and 10 to the minus 8 is 10 million times smaller than 10 to the minus 1. So yeah, it looks like a pretty darn good approximation to make. All right, that saves solving a cubic equation too. Now, compare it to pure water, right? So when we let it dissolve in pure water, we saw a molar solubility of, what was it, 3.3 times 10 to the minus 4 mole per liter. So we can see that this is somewhere on the order of 20,000 times less soluble in sodium fluoride than in pure water. And again, we can rationalize that using Le Chatelier's principle. If we increase the concentration of fluoride, if we have an ion in common, it's going to push the equilibrium back. It's going to make it less soluble. And we can see it's 20,000 times less soluble when there's already fluoride present as opposed to when we had pure water. Wasn't that neat?